All right, well, hello everyone, and welcome back. In this video, we are going to continue our discussion about AC circuits and focus on what's called the frequency response. So here's our goals for today's video. First, we will review some key applications of the AC circuits that we've covered, including using AC circuits as filters and other devices that are sensitive to frequency. We'll also learn about what the frequency response is, and we will see how we can calculate the frequency response for a given AC circuit. Finally, we'll also describe some important properties of filters made using AC circuits. So before we get into frequency response, let's first briefly preview where we are heading in the rest of the course. We have now learned a lot of tools about how to solve AC and DC circuits. The rest of the course is now going to focus on important applications of these AC and DC tools. So today we are going to focus on this first item. We're going to focus on how we can use what we've learned about AC circuits in order to study frequency response and design filters. Then next time we're going to start looking into things related to power, including AC power, complex power, power factor, and power factor correction. And finally, our remaining videos will focus on maximum power transfer, power distribution, transformers, and an introduction to devices. So why does all this stuff matter anyway? Why would we bother to cover all of these applications in our circuits curriculum? Well, one reason why, of course, is so that students who take circuits class for transferring fulfill transfer requirements. But another important reason is because these topics are really important. The National Academy of Engineering, or NAE, has outlined 14 grand challenges of engineering. You may have heard of these grand challenges before. The 14 grand challenges are 14 key challenges that the National Academy of Engineering thinks engineers must urgently solve. And if you look at this list of NAE's grand challenges, you can see that many of these grand challenges very directly are related to circuits. And so as we continue to learn about applications of our AC and DC circuit tools, let's keep these grand challenges in mind. Even if you're not ultimately planning to become an electrical engineer, chances are our knowledge that we've gained about DC and AC circuits could be really helpful if you choose to try to solve one or more of these challenges. So let's just do a quick review before we move on to frequency response. In our past few videos, we have learned how we can apply our favorite DC tools to AC circuits. And so we can now take all the tools that we learned from our DC circuits, like Ohm's law, voltage current division, superposition, all these tools, and to solve an AC circuit, all we need to do is express our circuit in frequency domain, and then solve for unknowns using impedances instead of resistances. So make sure you've reviewed our previous lectures on AC circuits and that you understand how to use our DC tools to solve AC circuits. We'll see that for the rest of this course, we're going to continue applying all of these skills to help us solve AC circuits. Let's also briefly remind ourselves of how we plan to solve typical AC circuit problems. You'll remember our general strategy is that we first need to transform everybody to frequency domain. That means we write our currents and voltages as phasors, and we also have to find impedances of each component. And we use those impedance equations that we've covered. Finally, once we have our impedances and our phasors in frequency domain, we can determine the desired unknowns using our favorite AC and DC tools. Finally, once we have solved for our unknowns, we transform our solution back into time domain. So make sure you're comfortable with this process. And if you need any review, please review our previous videos prior to continuing on with this video. Alright, so our last item to review before we cover frequency response is our equations for inverting and non-inverting amplifiers in AC conditions. You'll remember in our previous video, we learned that inverting and non-inverting amplifiers have their behavior governed by these two known equations. And so you'll remember that if we can recognize that we have one of these amplifiers in our AC circuit, and if we're able to assume that amplifier is ideal, we can directly use these amplifier equations to help us solve for any unknowns. Alright, so let's do one quick review question before we move on to frequency response. In this question, we are given an AC amplifier circuit, and we're told that the input is given by 1.2 cosine 400t plus 20 degrees volts. We see our resistor is 48 kiloohms, and the capacitor has a 25 microfarad capacitance. We are also told to assume the op-amp has ideal behavior. So in this question, we're first asked to transform the circuit to frequency domain, and then determine our output voltage, Vout, as a function of time. Let's go ahead and give this example a try. If you'd like, you can try pausing the video and see if you get the same thing as I did. Okay, so our first step is to transform to frequency domain. And I'm also going to go ahead and apply my box trick as well. So we see in frequency domain, our input voltage Vin of t, that Vin is going to be equal to 1.2 angle 20 degrees volts. As if we convert our cosine to a phasor, we take our amplitude 1.2 and our phase angle 20 degrees. We're already in cosine, so we do not need to adjust our phase angle. Next, we have our resistance R, and we know the impedance of a resistance will just be our resistance value, which is 48,000 ohms. And the impedance of our capacitor, ZC, that's going to be equal to 1 over j omega c ohms. In this case, our omega is 400. And we know that our capacitance C is 25 microfarads, or I'm sorry, 0.25 microfarads. Remember, being mindful of units, that's 0.5 times 10 to the minus 6 regular farads. So if we go ahead and substitute that in, we'll determine our capacitor has an impedance of 1 over j times 400 times 0.25 times 10 to the minus 6 farads. And if we plug and chug, solve for J, we get negative J 10,000 ohms. And finally, of course, our V out is unknown. I'll just leave it as an unknown phasor V out, and we'll solve for that in the next step. So we've successfully converted to frequency domain. Let's now find the output voltage V out of T. All right, so we could do node analysis or use some of our DC tools to find V out of T, but it turns out there's an easier way. Do we know what this amplifier circuit is? You may recognize this op-amp as a non-inverting amplifier. And we know from those equations that we learned in our previous video, we know that this non-inverting amplifier must follow this relationship. So we know the ratio of our output to input voltage will be Z1 plus Z2 divided by Z1. Here Z1 is the impedance of our capacitor, Z2 is the impedance of our resistor. Well, that's convenient, so all we need to do is substitute. In this case, we'll use Z1 is equal to negative J 10,000, and Z2 is equal to 48,000. And we can solve for V out. So let's go ahead and give this a try. Based on that equation, we know that V out must be equal to Z1 plus Z2 divided by Z1 times our input, in this case is V in. So if we math that through, we will get up top we have negative J 10,000 plus 48,000 divided by negative J 10,000 times our V in, which is 1.2 angle 20 degrees. And units here are volts and ohms. So we'll just need to use our polar converter, and we can determine that the upper part of this numerator becomes 49,000 angle negative 11.768 degrees. And the denominator becomes 10,000 angle negative 90 degrees. Notice that normally this would be negative 10,000 angle positive 90 degrees, but I rotated 180 degrees to make the amplitude positive. And then finally, I multiply that by 1.2 angle 20 degrees volts. And this just becomes a quick multiplication. We'll determine the final result will be 5.88 angle 98.232 degrees volts. But are we done yet? Notice we need to write our final answer as a function of time. So we need to convert back to a sinusoid. And so if we do that, we determine our V out will become 5.88 cosine. What's our frequency again? It's 400. And there you have it. Notice that that op-amp equation that we learned earlier is really handy for helping solve these op-amp problems. All right, so let's now continue on with our new topic for today, which is frequency response. What do we mean when we say frequency response? For the purpose of an AC circuit, the frequency response describes how a circuit's behavior changes when we change the input frequency. So remember, when we say input frequency, we mean that omega value. And so when we calculate frequency response, we use what's called the network function. And we give network function capital H as the symbol. So if you're ever asked to calculate the network function, that's basically the same thing as finding frequency response. And it's actually very straightforward to calculate network function. Mathematically, we say the network function is the ratio of our output phasor. In this case, we called the output Y. So it's output phasor divided by the input phasor, X. And so notice in this case, the phasors X, Y, and H, these can be currents or voltages. So depending on your problem, depending on what you're trying to solve, you might be dealing with both currents and voltages, or just one of them in this calculation. So if you see that you need to calculate frequency response, you should immediately be happy. It turns out that it's actually very easy to calculate the frequency response. I like to break it down into these 3 steps. First step, you want to make sure you've transformed your circuit into frequency domain. And depending on the information that you're given, your phasors and impedances, you may sometimes need to leave them in terms of frequency. Because remember, your goal is to find the behavior as a function of frequency. So sometimes you want to be very general here and calculate the impedance for any frequency omega. The next step in frequency response calculation is you need to identify your input and response variables. Remember, your input is basically going to be your x of omega. Your response is basically going to be your y of omega. And depending on what you're trying to solve for, those might be certain parts of your circuit or other components. And finally, in the last step, all you have to do is use our frequency response equation. We know frequency response will be the ratio of our response y divided by input x. So all we need to do is divide those two, and that will give us our network function, or frequency response h, in terms of our desired quantities. Let's go ahead and try a short example. In this example, we have the circuit shown here with 2 resistors and an inductor. And we are told that the input to this circuit is the voltage of our voltage source. The output is our voltage across R2. So notice when we calculate frequency response, we are going to want to specifically find the ratio of, in this case, our output across that resistor R2 and our input being the voltage of our voltage source. Notice we are also given some information about R1 and R2 and the inductor. We do not know what our input sinusoid is, but we'll see later in the calculation that that's actually not going to be a problem in this case. Let's go ahead and follow our 3-step procedure and determine the frequency response. So remember, the first step is to transform our circuit to frequency domain. All right, let's go ahead and draw this in the frequency domain, and I will also apply my box trick. So in frequency domain, we do not know what our input voltage is. It was not given to us. Let's just leave it as V in. Resistor R1 is just a 4 ohm impedance. Resistor R2 is a 6 ohm impedance. And our inductor impedance is J omega L. And notice here we don't know our omega. But that's okay. Because remember, our goal is to get a function of frequency. So we do expect our final answer will be some expression in terms of frequency. And in this case, we do know our L value. L is 8 henries. So in this case, we can just say impedance is equal to J times 8 omega. So now everyone is in frequency domain. The next step is to identify. We want to identify the input and the response. And in this case, we are given the input to our circuit. Input is our voltage V in, and our response is given as the voltage across R2, where R2 is our 6 ohm resistor. We don't know V in, so let's just leave it in terms of V in. And our response, that's just going to be the voltage across our 6 ohm resistor, or 6 ohm impedance. And wait a minute, we know what that is. How can we find the voltage across our 6 ohm impedance? How about voltage division? By voltage division, we know the voltage will be our 6 ohm impedance divided by the sum of the other series impedances. And then, of course, by voltage division, that whole expression must be multiplied by Vin, because Vin is our source voltage. So notice in this case, it's actually okay that we don't know Vin, because later on, if we divide our response by our input, the Vin terms will cancel out. So finally, our last step is to determine the ratio of input and response. So in this case, h of omega is going to be our response, y of omega divided by x of omega, where our input Vn is our x of omega, response is our y of omega. If we go ahead and substitute everybody in, we determine our frequency response is the following. So notice in this case, our frequency response is actually independent of our input voltage source. It completely depends only on the frequency of that input voltage source. So why do we bother to learn about frequency response? It turns out one of the most important applications of frequency response is designing circuits which are sensitive to different frequencies. And you can imagine that being able to amplify or block out certain frequencies is incredibly important in many applications, like communications, medicine, instrumentation, music, all sorts of applications. And so we've introduced a few of these filters during our lab, and so some of these might be familiar to you. You'll remember that a low-pass filter is a filter that allows all frequencies below some cutoff frequency to pass through. So anything lower than some cutoff frequency is able to pass. But once we hit that cutoff frequency, then anything above that cutoff frequency will be suppressed. Next, we have high-pass filters, which do the opposite. High-pass filters only allow signals above a cutoff frequency to pass through. Bandpass filters will only allow a certain range of frequencies to pass through. So there's kind of a minimum and maximum frequency that is allowed to go through. And finally, band-stop filters will prevent a certain range of frequencies from passing through our filter. So depending on what you're trying to do, you may need to design equipment or circuits with one or more of these filter types. You'll also remember that since capacitor voltage and inductor current cannot change instantaneously, it's impossible to get a filter which has this perfect behavior. You'll see all of these figures show an ideal example of the filter, where we completely block the undesired frequencies and completely allow the desired frequencies. But in real life, we see that very often we get something that is sort of a smoothed out version, where in real life maybe we have a more gentle. So in real life, we can't get perfect ideal behavior, but we can certainly try to come as close as we can given the needs of our application. There's a few other important parameters that come up when we talk about filters and frequency response. First one is gain. Gain tells us how much our input signal is increased or decreased by the filter or by that frequency response circuit. And basically, it's the ratio of our output amplitude to the input amplitude, or if we use our network function, we see that we just take the absolute value of our output phasor divided by our input phasor. Phase shift is interesting as well. Phase shift tells us how our output signal's phase changes compared to the input. So remember, when we talk about phase here, we're referring to our phase angle theta. So here we see that our phase angle is going to be given by the difference between our output phase angle minus the input phase angle. So in this case, we'll take our phase angle of our output and subtract the phase angle of the input. One other important parameter for filters is producing what's called a Bode plot. And Bode plots are very important in designing filters for certain applications. And essentially, how you make a Bode plot is you plot the gain in decibels. And so that's basically our amplitude ratio. We plot that versus the logarithm or log of our frequency. And typically you see that a Bode plot will sort of have this flat hill shape. And we see that the maximum of the Bode plot tells us the frequencies that pass through our filter best. Here's a few more important filter parameters. First one is bandwidth. Bandwidth is important for bandpass and bandstop filters. And in a bandpass or bandstop filter, the bandwidth tells us basically the width of that filter's peak at half the maximum. So if our filter had the behavior shown in this curve, where this was our amplitude ratio or gain on the y-axis and frequency on the x-axis, bandwidth basically defines what range of frequencies most easily pass through. So bandwidth tells us what frequencies most easily pass through the bandpass, or what frequencies get blocked by the bandstop filter. Bandwidth is defined as the width of our filter's peak at 50% of the maximum, or the full width half maximum value. And bandwidth is measured in frequency units. Bandwidth is important because it basically tells us what range of frequencies will be most easily passed through or blocked. Generally, you want the bandwidth of your filter to be relatively narrow because you want your filters to be very selective for the frequencies that you want to amplify or block. Typically, we want our bandwidth to be relatively small. If our bandwidth is too wide, then we might allow undesired frequencies to also pass through, which defeats the purpose of the filter. Next term is resonant frequency. You might remember resonant frequency from our second-order differential equation. Remember that omega naught term when we were solving second-order differential equations? That's our resonant frequency. So often we see resonant frequency appear in filters and AC circuits that are based on second-order circuits. Resonant frequency is the frequency at which we get the highest possible gain, or at which we see the highest amplitude of our output. Resonant frequency is very important because if we want to design a filter to amplify or block certain frequencies, we want the frequency of interest to typically be our resonant frequency. Last term of interest is called the quality factor. The quality factor is the ratio of our resonant frequency divided by the bandwidth. Quality factor basically tells us how selective our filter is. Quality factor is a dimensionless number, and most of the time we want our quality factor to be as high as possible. The higher the quality factor, the more selective we are for the resonant frequency, and the narrower the bandwidth of undesired frequencies that are accepted. So why should we care about all these filter properties? Well, if you ever need to amplify or block signals, you probably need to know about filters. And you may find yourself in a position where you need to design or purchase a filter in order to help your application. Remember, generally, the higher your quality factor, the better your filter will be, because it will be more selective for that desired resonant frequency. So for electrical engineers and people in communications, it's especially important to design filters which operate at certain frequencies. You can see in this figure an example comparing a high Q filter and a low Q filter. We see that a high Q filter, given that it has a very narrow bandwidth, the peak of the amplitude versus frequency plot is very sharp. The high Q filter is very selective for its resonant frequency. On the other hand, the low Q filter has a very wide peak, so it's not as selective for the desired resonant frequency. Let's go ahead and do one more example of frequency response before we move on. In this example, we are given that the input of our circuit is that source voltage Vs of t. We are told the response is the mesh current I of t. We are also given that our resistance R is 30 ohms, L is 2 henries. Notice we are not given Vs of t, but let's go ahead and solve everything in terms of omega and Vs of t, and we'll see that we'll still be able to determine our frequency response. And then in the second part of the question, we will find the gain and phase shift if our input frequency is 20 radians per second. So once again, let's go ahead and follow our frequency response procedure. Our first step is to transform our circuit to the frequency domain. And so to do this, we go ahead and draw our circuit and apply the box trick. And in this case, we have our source Vs. We have our resistor R, which is 30 ohms. And we also have our inductor L, which has a 2 Henry impedance, or 2 Henry inductance. So we know that our impedance must be J omega L, or in this case, we substitute in L is 2 henries, so that will give us J times 2 omega. And in this case, our response is the current I going through this circuit. So our second step is to identify the input and the response. And so in this case, our input is Vs, and our response is our current I. Do we know how to calculate our current I, given Vs and our impedances? Yeah, notice we do, right? We know our response I must be equal to our voltage V divided by Z. In this case, our response must be Vs divided by our 30 ohm resistor plus our J2 omega ohm impedance. So in this case, we know that our input x of omega is just Vs, and our response is Vs divided by 30 plus J2 omega. So now our last step is to find our frequency response. And we know our frequency response is just our output divided by our input. So in this case, our frequency response is given by our output, which is Vs over 30 plus J2 omega, divided by Vs. That gives us our frequency response is just 1 divided by 30 plus J2 omega. So we've completed the first part of this question. The next part of the question asks us to find the gain and the phase shift if omega equals 20 radians per second. Let's go ahead and give this a try. So let's first remind ourselves what gain and phase shift are. Remember that gain is basically the magnitude of our frequency response. So in this case, that's gain at omega equals 20 radians per second. So if we substitute in we can determine that our gain will be equal to just 1 divided by 30 plus 2 times 20 J. Well, in this case, we want to basically find the actual amplitudes of this numerator and denominator. So we could also write this as 1 angle 0 degrees divided by our denominator, which in this case is 30 plus J40. And in this case, notice we only really care about, for the gain calculation, we just want to know the magnitudes. So in this case, if we want to calculate our amplitude, we will see that we essentially have 1 angle 0 degrees divided by 50 angle 53.1 degrees, and we'll determine that our gain will just be 1 over 50, or 0.02 amperes per volt. So notice that the gain is calculated by basically dividing the amplitudes of the input and output phasors. So we divide our output amplitude of 1 and we determine our gain of 0.02. Similarly, the phase shift, that's the difference in our phase angles between the output and the input. So in this case, we see that our output Y is 0 degrees, and our input X that we're dividing by is 53.1 degrees. So we subtract 0 degrees minus 53.1 degrees. Again, that just comes from rewriting our gain in polar form. We can see what our amplitude and our phase angles are. So we determine that our phase shift equals negative 53.1 degrees. And there you have it. So once again, the gain is the ratio of our amplitudes. Our gain is the ratio of the amplitudes. And the phase shift is the difference between our output and input phase angles. Alright, so we mentioned that frequency response is really important for designing AC circuits which are sensitive to different frequencies. So to put everything that we've discussed together, let's briefly show an example of how we could design a filter using what we know about AC circuits, AC op-amps, and the frequency response. This filter shown here is a bandpass filter, similar to one you may have seen in lab. And you can actually use the inverting op-amp equation to derive the frequency response for this filter. And here, these two capacitor and resistor in parallel, well, that's just our Z2. And over here is Z1. So we can say V out over V in is equal to Z2 over Z1. And all we need to do is substitute in those separate impedances for Z2 and Z1, and we determine our frequency response. And then using these relationships, we can actually determine the cutoff frequencies, the low pass and high pass frequency, where that bandpass filter will allow frequencies to go through. And as long as we're between those two frequencies, we can also find our gain. So frequency response becomes really important if you're trying to design a filter which operates at certain resonant frequencies with a certain gain value. And you can see that by carefully choosing our capacitors and resistors, we can design a special bandpass filter optimized for a given resonant frequency and a given gain. Before we end for today, let's go ahead and cover one last important tool that we're going to be using in our next video. In the next part of the class, we're going to move on to discuss AC power. And in order to look at AC power and really understand it well, we need to use a tool called a phasor diagram. So these will be useful in our next few AC power lectures. And so to help us prepare for those AC power discussions, let's briefly introduce phasor diagrams here. Phasor diagrams are actually really simple. All they are is a graphical representation of phasors on the complex plane. Remember, when we say the complex plane, that means we're referring to that imaginary axis being our vertical axis, and the real axis being the horizontal axis. To make a phasor diagram, we just have to plot each phasor of interest on the complex plane. Typically, we consider each phasor of interest in polar form, but you can also use rectangular form if you prefer. You basically draw the phasor such that the length represents the magnitude of that phasor, and the angle relative to our real axis is our phase angle. So here's a procedure to help design phasor diagrams. The first step is to make sure that you have determined current and voltage phasors for each component in your circuit. Later on, we may also draw phasor diagrams for power and impedance. But you want to make sure you know your phasors, and you want to write them in polar form. Also remember, if you multiply something by j, that is going to rotate your phasor 90 degrees counterclockwise, because it will basically add that factor of -1, or factor of square root of -1, onto your phasor. Finally, once you have your phasor in polar form, you can directly draw your theta and A value for each phasor that you're interested in. Let's do a quick example. Suppose we have this RLC circuit shown here. We're given all the values of our resistor, inductor, and capacitor. We also know our current, and we know our frequency is 10 radians per second. If we were to change this circuit to frequency domain, we would be able to show that our current is given by 25 angle 0 degrees amperes. And using Ohm's law, we can find all the voltages across each component. So using what we've learned about phasors and complex numbers, let's go ahead and plot the phasor diagram for this circuit. The first step is to make sure you know the phasors for each component. So here we'll determine our voltage and current phasors. And notice this is done. These values were given. If you were not already given your phasors, you could calculate using AC tools and converting everything to frequency domain. The next step is to write each phasor in polar form. And this was also done for us in this question. If you needed, you could use the online phasor calculator in order to convert, or convert by hand. Finally, our last step is to plot each phasor on the complex plane. So I'm going to go ahead and draw my complex plane. Okay, let's go ahead and draw this phasor diagram. So remember, we have our imaginary axis being the vertical axis, and the real axis being the horizontal axis. And now we need to go through our list of voltage phasors and current phasor and plot each phasor on this plane. Our current phasor is going to be really small because it's only magnitude of 0.25. So we'll go ahead and draw our current phasor as a pretty short arrow. Next we have our resistor, and that one is a fairly long arrow because this one has a magnitude of 20. So that will be our blue line, and notice since VR has a phase angle of 0, it goes completely along the horizontal axis. Next, we have our phasor VL. That's the inductor's phasor, and we see that that one is 20 angle 90 degrees, so it's about the same length as our resistor. Make it a little bit longer, but it's going vertically. And then we also have our capacitor, which is 5 angle negative 90, and that's bringing our total vertical voltage down, such that here we have VL minus VC would be about 15 above the 0 point. And now we could actually see, if we were to kind of make a dotted line taking our net horizontal component, which is VL minus VC, and our net real component, which is VR, which is just 20, VL minus VC is 15, we could determine that our total VS, total series voltage, that is going to be equal to 25 angle 36.9 degrees. So if you actually did some vector addition using these phasors, you could actually draw in this triangle on the phasor diagram. So this is one example of how we can plot phasors on the complex plane in order to better visualize the interactions between the different components of our circuit. So you might be wondering, when will we actually use phasor diagrams in this course? Here's a sneak preview. In the next couple lectures, we're going to take a closer look at something called the complex power. And we'll see that by drawing phasor diagrams, it will help us visualize the interrelationships between real and complex components in our circuits. So please remember phasor diagrams because they will become more important in our next few videos when we start looking more at complex power and impedance. All right, let's go ahead and wrap up here for today. You should now be able to recognize some really key applications of the AC and DC circuit tools that we've covered. And even if you don't become an electrical engineer in the future, you'll probably find that what we've learned about circuits will be incredibly useful for many applications, including those grand challenges of engineering. You should also now be able to calculate frequency response for AC circuits. And knowing what we know about frequency response, we can also describe and calculate important properties of filters that are built using AC circuits. In our next video, we'll start applying these tools to AC power and complex power. Thanks everyone for joining the fun, and we'll see you in the next video.